Okay, why do an alkene, why do electrons attack H plus?
Why doesn't it charge?
Why does it attack H plus?
It's positive.
It's more stable to
Because the alkene is electrons and the H plus is positive, and the electrons like positive. Minus likes positive. That's organic chemistry. All right? Well, what does it have to be an H or can it be a C plus?
It can be a C plus.
It can be. It's the plus part that we're attacking. Doesn't matter what type of letter the atom has on its back, a C or an H or a Mg or, okay? Alkene can also attack C plus, and a C plus is called a carbocation. Let's look at this mechanism. This has two alkenes. React this with HI, we get this product. How in the world does this happen? Well, sometimes you can't start over here, as we've done. Would you like to make that carbocation for some reason? I would, because if I can make that carbocation, then I'm home free. All I got to do is have the I minus add to the carbocation, that would give that product, right? How are we going to get there? Well, typically I would tell you when you do mechanisms, you want to start at the very beginning and do one step at a time. But it is sometimes okay to look over there. But I wouldn't keep going backwards. Let's start here. What do we know? What's the electrophile here? H plus. Okay. We have two alkenes. Alkenes react with H plus. So we have a choice. Which alkene do you want to react? Well, just like if we were choosing between one alkene and saying top or bottom carbon, and you're looking at you want to make the best carbocation, the same thing here. You just have four possible sites. Of the four carbons of the alkenes, where do you want to make carbocation?
On the tertiary.
Right there? Well, let's kind of start there. Hopefully we may be rewarded. Because that's going to be the easiest carbocation to form, because that's going to be the most stable. And what did we say about transition state leading to a species? The more stable it is, the lower transition state. So this should have the lowest transition state energy, and thus be easiest to form. So we can show H plus, I minus. These electrons hinge away here, and we get now I'm going to draw this. Where's the plus at? Right there? Okay. Then we got 1, 2, 3, 3 carbons. 1, 2, 3. And then the double bond. But it's 3 plain carbons and then double bond. So the double bond is here. And I just did a different conformation. Okay? I just sort of switched that down a little bit. It's got a different conformation. Okay? Have we done anything odd yet? What do we do odd there?
You put the double bond, it's not really like a ring.
It's not really a what?
Because you put it on the outside, the little one's on the outside
On the outside of what?
of the ring.
Here? You mean draw it here?
Yeah.
Like that? There's no difference. Why does that look different? Okay. Well, there's no difference. Sometimes you'll see the double bonds drawn like this. Not even connected. But basically, it's it's carbon-carbon double bond. Okay. Now, I minus could attack here, you can get a product where you added HI, you did a hydrohalogenation. But that wouldn't be that over there. We got to make a 6-membered ring. How are we going to do that? Instead of I minus attacking, what else could attack this?
Carbon, pi bond.
What's in the heading up there? Pi bonding can attack the plus. Does pi bonds attack pluses?
Yes.
Just did it right here. This is going to be not an intermolecular. It's going to be what? Intramolecular. These electrons are going to break away. To make a 6-membered ring, which carbon do we want bonded here?
Outer carbon.
1, 2, 3, 4, 5. That one. They break away from that carbon down there, and this hinges away here. Okay? Somebody pull my arm and go attack that carbocation. Making bond up here, leaving this as what? Positive. What does that arrow mean? What does it give? It's going to give a 6-membered ring. All right. Sometimes it's best just to draw exactly that. But here we got another carbon. That's how we were, right? But this hinges up and makes bonds, and that's now bonded there, and that's plus. See my thinking? But now that's a 6-membered ring, right? 1, 2, 3, 4, 5, 6. It's a 6-membered ring with 2 methyls coming off of 1 carbon, and the plus 2 carbons away. I don't really need to redraw that, do it? Because this is what? That's equal. Okay? That's the same thing. So I kind of drew it. Basically, I erased this and hinged it up here, leaving that a plus, and that's that. So if you're working with pencil, you can just do that and then redraw it, because that is a 6-membered ring. So this gets us home free, because now what do we do? Say it with me. These electrons add to the carbocation, make sigma bond, and there you go. Right? There's your mechanism. There's your arrow movement for showing the question.
Is there anything discouraging, like some type of like super polymerization action with the different molecules doing this?
Instead of this alkene attacking the alkene from another molecule attack? Yeah. Yeah. All right, so this is a good point. An internal reaction is always faster. Okay? All right. So you're talking about another alkene attacking that plus. From another molecule? Okay. So you're another molecule. Hold your alkene in your arm here. Okay. And I've got mine, and we're like 2 angstroms apart. That's way apart. Okay. Here's my double bond. Here's my cation. There's your double bond. Okay. Now let's see which one attacks the carbocation faster. I did, because I'm right here. Internal's faster. If you want to come attack me, you gotta walk 2 angstroms over. Internal's always faster. Believe me. Okay. Aaron, let's clap hands. Hold your hands right here. Okay. That hand. Clap this one. I beat you. This one. I beat you because I'm right here. Internal's faster. Okay? That's faster than another molecule. Intramolecular is faster. But yes, polymerization can take place. You must have been looking down here. Down here, polymerization, cationic polymerization. If you take this compound here, treat it with an H+ catalyst, you can get a polymer. Alkene, slang for alkenes is sometimes called vinyl. Also sometimes called olefin. But vinyl you've heard, we call PVC, polyvinyl chloride. If that was a chlorine, that'd be vinyl chloride. And if we polymerize that, we'd get PVC. I just don't have a chlorine there. So how does polymerization take place? Well, it's the idea that was just brought up. Okay? Alkene H+. Do you know any chemistry here? Sure. This is going to attack H+. So you're going to leave carbocation in middle or right? Middle. So this hinges away from a middle. These electrons attack here, giving this carbocation. Okay? This may be the last time I say this. But there's your new H. See the new H? 2 there, there's now 3. All right? I'm not going to say that again. You got to keep track of your H's. Because I know a lot of you are looking at that and like, how did that form? You've got to know this at this point. Okay, what can attack that?
Another water bond.
Well, some type of, okay. Now see, this is very generic. If we add water, it can attack it, and you can get an alcohol. If we add an I- or something, that can attack it. It's got to be a minus here. You cannot go to the stockroom and say, give me some H+. They're going to give you some minus with it. Okay? So choice of acid is important here. What we want to happen to get that is we want another alkene to attack it. But here it's not going to be intramolecular, it's going to be inter. This can attack here. Now if this attacks this plus, this could be an H+. It's just bigger than that. Now we're focusing over here. Are we going to leave cation on top or bottom? Bottom. So it hinges away from the bottom. These electrons hinge away and attack here. What does that give? Well, I'm going to draw the original molecule, the nucleophile molecule. That's the nucleophile, this is the electrophile. We got this. Which carbon of this, 1, 2, or 3, bonds to this over here?
Because it's hinging from the 1.
Right. This is 1 and 2. And I hinged away from 2 and went and bonded to that thing. So is that carbon bonded to that thing? No, the upper carbon is bonded to that thing. This thing is left without. Okay? So you got to know these things. This is fundamental. But that right there, moving through organic 1 and 2, you got to know what's reacting with what. Hinging up. So now 1, 2, and 3, what is 2 over here now? Cation. 1 is bonded to what? You may call that A, B, and C?
Bonded to B.
It's bonded to B. But B is like this. A, B, and C. Right? Now I like to do this. Especially we get a lot of bond. Which bond did we just make? The B to C bond? Obviously it's what? 1 to B. I like to just sort of do a little, that's the bond we just made, right? Am I agree that's it? Okay. Now what can happen? Now we got another carbocation. What can attack this?
Another alkene.
Joe?
Another alkene.
Yeah, because what are we doing? Polymerization. What is polymerization? It's where molecules just react over and over, like 100 gazillion times. All right? We did it once. Let's do it 999 gazillion more. You ready? All right. So, that attacks here. I'm going to call this X, Y, and Z. What's going to bond here? When this reacts, are we going to leave cation on X or Y? Y. That wasn't a question. So it comes up here. So these electrons break away from Y and come up here. What does that give? Let's see. We got boom, 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 boom. And that's 1, 2, and 3 there, that's that. Now bonded to 2 is what? X. And X is bonded to Y and Z. X, Y, and Z. What bond did we just make? X to 2. And in this reacting alkene portion originally, where's the carbocation? On what? And if we want to show the original bond, we're making these bonds. Okay, what do you want to do next?
Another one.
Now we got to do it 998 gazillion times more. Do you get the idea? What type of acid do you want to use? Do you want to use HBr? Why not HBr? Taylor? Why not HBr? Because Br minus would add to the cation. You don't want something added to the cation. You want this to add to the cation. You don't want a competing nucleophile. So what type of acid do you want to use? Name an acid that would be good for this. HF, why? It's strong, but HBr is a stronger acid.
With the X on the reactor.
Because the S won't react. You'll just leave the alkene to react. Okay? Or sulfuric or phosphoric. Okay, the ones that won't react. So your choice of acid is important. Would you like to keep this dry or would you add water to it? Okay, water would be a nucleophile. So a dry, strong acid, HF would be good.
So what does that mean, a dry, strong acid? How does that reaction actually take place?
How's it what, Mert?
So you just put it in something that can dissolve the HF that's not water? Is that what you mean by dry, strong acid?
Yeah, dry organic solvent. Let's see. How do we show this other than just being it so long, long, long? We look for repeating units. Okay? First off, what started this whole shebang? The H plus. And H plus, is that a cation or anion? Cation started it. That's why it's called a cationic polymerization. Okay? Cation initiated this. If you do a polymerization with hydroxide, that would be an anionic polymerization. Okay? Initiated by a cation. So, where's the new H at? Tell me where it is over here. What atom? If we had labeled this A, B, and C, it's on C, right? I'm going to draw in the new H. Okay, here's a new H. If we come over here, the new H is here. What do we have? We have the H. Then look at this. We have CH2C-methyl. 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 And if you keep going, you'll have the H, and then you'll have CH2C-methyl. CH2C-methyl. The CH2C-methyl is your repeating unit. And here I've shown that, the H, and then the CH2C-methyl. Put parentheses around it, and really if you show this, you don't even need to show that. The polymer is just sort of shown like that, and the N means what? Some huge number of repeating. N is never defined, it's just huge, generic, okay? Now polymer chemists, there's a lot more to this. How long is the chain? Do you get branching? And the way you do the polymerization gives you different lengths of polymers, and the different lengths give you different properties. Okay? That's a huge science. A lot of these end up being like plastics. Do you want a soft plastic or a more hard plastic? It all depends on the polymer chain length. That depends on the conditions.
Now, real quick, are we doing, is it CH2CH methyl or CH2C methyl? Is that really good?
Well, there is an H on there. Yeah. Yeah, I just didn't quote it. Okay. CH2 C methyl, but yeah, there is an
Oh,
H.
but you're just drawing it anyway, you're not actually writing the CH2C.
Right, yeah, you're right, I didn't quote that second H, it's there though. Okay? That would be a polymerization. So on that page, we looked at alkenes attacking carbocations, either intramolecularly or intermolecularly. Y'all know what THC is? Tetrahydrocannabinol?
Yeah.
Cannabinol? Don't know what it is? Okay. Y'all do. I just don't want to say. Nobody knows? It's what? Heard about it. Okay. All right. It's marijuana. Okay. It's the major component. Marijuana. Okay. Right there. It's made. Okay. The marijuana plant makes it from this. How does it do it? Well, you can show a mechanism for it. Okay? Show a mechanism for it. Now, it's amazing that that little plant with the little leaves on it can do chemistry like this. Okay? All it takes is a little H+ catalyst. So try that mechanism. You can make your own THC. Okay? All right. We've covered number 1. We're now going to be moving to Roman numeral 2. Reactions involving other electrophiles. Actually, up top, we also did C+. Other electrophiles. And these reactions do not involve a carbocation intermediate. All the ones before have. Since there's no carbocation, they will not rearrange. Because you only get skeletal rearrangements when you have carbocations. Okay? It's amazing the information is really. Okay? So, here are the reactions. I reckon you can come back and look at these. I'm not going to just go through them here. We're going to go to the other sheet. First one we're going to do is one you will also do in lab is react the alkene with not HX but X2. It's like Br2. We're talking about just halogen. Diatomic halogen, Cl2, Br2. And that's going to give 2 X's across the pi bond. A dihalide, trans. We'll be doing all these. There you go. Now I know a lot of times you look at this and it's like brand new or, okay, you should have looked at this before. But certainly once we go through things, you then look back at this and it becomes a review. Right? Okay, first is the anti-addition, anti or trans addition of X2 to alkenes. X2 is mainly going to be chlorine and bromine. Iodine doesn't work here and because it's too sluggish. F2 doesn't work here because it's too reactive. Fluorine is just too hot to handle. Fluorine causes lots of explosions because it reacts so violently. Okay, alkene is going to react with chlorine. It's one of the easiest reactions we'll ever do. You're going to end up with chlorine bonded to each carbon. Okay, chlorine bonded here, chlorine bonded here. All right. But mechanistically, how does it happen? There's also going to be stereochemistry. But in terms of putting the 2 chlorines there, that's easy. What you don't have to decide is which carbon gets a chlorine. Both, okay? With HCl, you have to decide which carbon gets the H, which carbon gets the Cl. By the way, in your textbook, you'll see something called Markovnikov addition. Okay? I don't tell you what that is because it's nothing but a crutch and it makes you try to memorize. It tells you that the H ends up on the, which carbon. I don't even know.
So we use there.
Yeah. I don't know. I know mechanism, and I'll tell you where it's going to end up because I know the mechanism. All right? Things like that just sort of promote memorization. So I'm not going to be covering that Markovnikov term. We may mention it at some point because as an organic student, you do need to know what it means. But don't rely on it. Okay, how does this work? Let's look at chlorine. With HCl, we clearly have a dipole. And this is clearly partial plus. And you also know this can be ionized, and we can just ionize it and make this. So here we clearly have electrophile, something that would like electrons to attack it. Why would these electrons want to attack chlorine? Chlorine looks like it's nonpolar, right? Indeed it is, officially nonpolar. But your halogens are known to be polarizable, okay? They're both kind of stubborn, okay? Yes, they can be bonded very nicely in a nice symmetrical bond, but see those chlorines are like stubborn. They're always pulling on each other. And as this guy pulls, for some reason, I don't know why, that guy becomes a little partial plus. It's called polarizable. That's just something you have to kind of, okay? So, why would we do that? I'll just polarize it. So, here we go. These electrons can attack the chlorine. What you will not show chlorine is, never show it ionic. Never show it Cl plus, Cl minus, like we did this. It has to stay covalent. But these electrons can attack the partial plus, make the bond to chlorine. These electrons will move on to the chlorine. That's what your arrows mean. All right? So I've got it drawn out here for you. What does that give? Electrons attack chlorine. We make the bond to chlorine, leaving that as a carbocation. All right? We also kick off the other chlorine, so we've got Cl minus. Carbocation, how would we get final product? Cl minus could attack carbocation, and that would give us this. Okay? Problem is, that's not the mechanism. And we know that from stereochemistry, and we'll talk about stereochemistry below. The stereochemistry says we need another mechanism. And the actual mechanism is right here. Which is going to attack the carbocation faster? The chlorine that is bonded to it right next door, or the chlorine way over there? Yes. So doesn't this make sense? The chlorine that attacks is not that one, it's the one connected. It attacks. And I call this back bonding. Most books probably won't say back bonding. And when that attacks, what do you get? You get a three-membered ring. Okay? The electron's bonded there, but now the chlorine has a positive charge. This three-membered ring, which has been observed, actually also by crystal structure, and we know this is formed, is called a chloronium ion. If it was bromine, it would be a bromonium ion. It's called a bridged three-membered ring with a halogen. From there, now the other chlorine comes in, and this is our first look at a nucleophile attacking not a carbocation, but attacking a tetrahedral carbon that doesn't have a formal plus. This attacks here. These electrons make bond here, but something has to leave because that carbon can't make 5 bonds. So it kicks these those electrons off. That moves on to the chlorine as a lone pair, and now you have that. The 3 lone pairs on each chlorine. Why would this chlorine attack that carbon? Is there any plus charge here? There's not a formal plus. But what do we know about chlorine? It's electronegative. But that's a positive chlorine. How electronegative is that going to be?
Still more than carbon.
A neutral chlorine wants electrons. What do you think about a positive chlorine? It really wants electrons. Okay? There's actually a lot of partial plus here because of that dipole. Alright? The important thing is this comes in backside. This is really test 3 chemistry. When we get to test 3, we'll talk about backside, and I'll remind you of this right here, and you will not remember. Okay? Whenever you attack a tetrahedral carbon, a 4-bonded carbon, and kick off, what do you want to say? What do you want to call something that leaves the carbon? Let's call it a leaving group. Whenever you attack a tetrahedral carbon and a leaving group leaves at the same time, you do it backside. What does backside mean? Pretend the chlorine is bonded to you, Zach. Show the chlorine. You can point it forward if you want. Okay? Now I'm going to go bond to him, and I'm going to kick off that chlorine. How am I going to bond to him? Starts with a B. Backside. So am I going to bond over here? No. I'm going to bond back here. Now, that's not backside just because that's his back. Do your arm like this. Okay. Pretend to do it like that. Okay. There you go. Pretend the chlorine is like that. How am I going to approach him? I'm going to approach him here. The backside refers to opposite of where the leaving group is projected. Okay? The leaving group is bonded up. How is this going to come in? Down. Down this backside. Okay? So it's down, and you get to... Now here, it's not really relevant because of the stereochemistry, but in the next couple of examples, you'll have to know how it attacks, and it attacks backside. Okay? All right. Now, why does it attack over here and not over there? Because there's also pooling on that carbon. Okay? Here, I'm the chlorine, and y'all are 2 carbons. Okay? And y'all are bonded together. 3-membered ring here, and I'm the chlorine, but I'm positive, so I'm real mad. And I'm like, give me some electrons. You may even wonder why I wanted to bond, but it does. Now, you're bonded to a methyl, actually 2. Okay? All right. So which carbon is more willing to take on plus? The one with the methyl bonded to it or without?
No.
The ones with. This carbon's more willing to take on plus because what do these friends do? What do we know about sp3 carbon?
No, you literally don't.
These donate, right? Okay? Because she donates to you, and there's actually 2 of her, you're more willing to say, okay, chlorine, you can have some. And so we barely hang on because you're getting electrons from her. There's more polarization here, there's more partial plus here. That's why it attacks there. It's kind of shown over here. Okay? These 3-member rings are really strained. Are you going to have more strain on the bond over there, leaving more plus there? Or more strain over here, leaving more plus there? That. Why? Because you got more rich friends over here. The chlorine wants to borrow money. Is it going to borrow money from this carbon with 2 rich friends, or this carbon? It's a better scenario over there. Okay? Ultimately, which carbon do we attack here? The more substituted. Okay? Because of this. Because that's the carbon they can take on more plus. More plus builds up there. Show products down here. Now, that's this Br2. This is an interhalogen. We're going to have to think about, there you have to kind of wave your hand and say there's a temporary dipole on this polarizer. Here we actually have a dipole. How's the dipole here? Which halogen is partial plus? Okay. You guys do the Br2, you guys do the ICL. And there's actually no stereochemistry here. The one with the BR2 is easiest reaction organic chemistry. There's no stereochemistry there. I'll tell you when we have stereochemistry. The next ones will have stereochemistry, and that's when we will have to really consider the backside attack.
With this in the Van der Waals portion, you seem pretty like suspect of the idea of electron shift or like temporary dipoles. Is there a? I was just curious as to if that's true or if there's like kind of a reason behind that in chemistry. Like if there's another thing that seems like it's more legit. Or am I making this up?
I don't know. I don't have a good explanation. Why BR2 is polarizable?
No, why, I would say it didn't seem like you liked the electrons being more intense on one side at a certain period of time. It just kind of seemed like every time you bring that up, you didn't like that concept.
I'm not quite sure of your question.
Okay.
Some issues in science are not concrete, they're debatable. You can look in the literature and see what the latest arguments are. What we know is that it reacts. Since it reacts, we have to explain it. So what's your explanation? It's got to be something to generate some dipoles, because ultimately pluses react with minuses. If you say BR2 is nonpolar, then it shouldn't react. Why would it be attracted to the alkene? So you can call it polarizable, and usually that's put in quotation marks because it's sort of a little suspect, not clear. Okay, what we got up top here? We just had BR2 across the pi bond. We make a, what are we making here? You need to know terminology. Okay, terminology, what we're making. What do you want to call that product? It's a dibromide, a dihalide. Okay? Now, do we call it trans? Not here because there's no stereochemistry. We'll see when we need to call it trans or anti. Okay? We just added BR2 across the pi bond. Mechanistically, I forgot to say something up here. Nobody asked me. Why didn't y'all ask me about that one up there? Because we're under Roman numeral 2. What does it say about carbocations?
No carbocation.
No carbocation. So why didn't somebody ask me why I made a carbocation? It's a big thing, and I should not have forgot to cover it. That's because this is not actually formed. And this is my term. You're not going to see this in the textbook. NAF, not actually formed. There's no carbocation here. There's only one intermediate in this reaction shown, and it's the chloronium ion.
How is that possible?
That's because the first two steps that I'm showing are concerted. What does concerted mean? They happen at the same time. Okay? And this is huge. See, what happens is, as soon as the pi bond attacks the chlorine, the new chlorine is back bonding. These two steps are concerted. Okay?
So with the cation will be the transition state or nothing?
Let's illustrate it with my little, very sophisticated arm movement. Is that right, Shana? Okay, you're the chlorine. All right. You bonded to the other chlorine. All right. Okay. I'm the alkene walking down the road. You like pulling in because y'all don't get along. And I'm going to attack you. Kick electrons out. You become Cl minus. But now I'm bonded to you. And here's a carbocation. And that's what we showed in the first step. But I'm telling you that's not what actually happens, because the second step happens at the same time. Here's the carbocation. What's the second step? You then back bond. Okay? But instead of it being two discrete steps, it all happens at the same time. Okay? As soon as I attack you, you attack me with this hand. Okay. Here we go. As soon as I start going do 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 do, you go. Okay. Do 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 do. All right. And that cation never formed, because as soon as everything happened, it's all transition state. As soon as I bonded to you, you bonded to me, and we went straight here. Straight here. Two steps happened at the same time. Why do I show it like this? Because I feel if I do it all and go straight there, it's like doing this and you get confused. So I feel like let's show it one step at a time, but what you have to show here and understand is, you use this term, NAF. Not actually form, the chlorine immediately back bonds, and this is the only intermediate. Because, how do we know carbocation didn't form? There's multiple reasons. Stereochemistry, there's no rearrangements. Okay, we'll clarify that. Ultimately, how many intermediates in that reaction up there? There's only one. So if you were to do a reaction coordinate diagram, you'd only show one intermediate. And it's the chloronium or the bromonium. Okay? NAF.
So using the
None of these down here have carbocation, but guess what? I'll show it, and I'll say NAF. Because all of these are going to involve back bonding. And if something happens at the same time and you don't actually get that. There's that one. Product here. You don't just put two halogens on the carbon. Which carbon does the iodine end up on? Let's do it mechanistically. It's like me asking you what's 55 times 55, and then you're like, hold on, let me do this first, right? All right. You're not just going to spout off that it's 3025. This attacks which halogen? Partial plus. Are we going to leave plus on right or left?
Left.
Left. So this attacks here. And we attack the iodine. When we attack, we kick that off. We attack the iodine, and this is a plus for us on the board here. But then we have to say, is this actually going to form, or is the new thing going to back bond? The new thing's going to back bond immediately. And what do we get? We get an iodine that has 3 bonds and a plus, and that's called an iodonium ion. And this is NAF. Now we have a Cl minus. And this iodine can pull on either carbon. Which one does it pull more on? The one with the rich friend or not? Whenever you attack a bromonium ion or a halonium, which carbon do you attack? More substituted. So we attack here. And we know we do it backside. It's not really important here, but That bond is down, so we're going to come in here and kick that off. What do we call a group that leaves when we get kicked, when something comes in? Yeah, the I plus is the leaving group, and what does that give? It's going to give you a product. So the iodine is on which carbon? Left or right? It just opens up. It used to be back bonded here, but what's now bonded here? Chlorine. And there's your product. Now you may ask, why is the chlorine down? That's because it does not matter. Okay, we'll learn when it matters. Okay? All right? It's kind of like asking me, why is my thumb forward? It don't matter. It could be like that. Okay, either way. The important thing is, why do we not get chlorine here and iodine here? Because the mechanism doesn't dictate that. So this reaction is regioselective. The chlorine ends up bonded in that region. Is this reaction regioselective? It's really not. I question this is kind of stupid up here because there's no alternative. Br on each carbon. But down here, the question is valid. Everybody see that? It's all because of your mechanism. Let's take a 3-minute break. Questions? It's still the same comment. You're shifting two currents. While that's sometimes possible for us.
I got the same thing, but I had the chlorine attached with this.
Which is faster? Which is going to attack the plus faster? Chlorine, which may be 2 angerons away, or the iodine is sitting right here. So it's like, it's just a physical phenomenon that you can't ignore. It's like, okay, I know you have electrons, iodine, but I don't want you to be attracted to this plus. You can see. But there's other reasons, because we know that the chlorine has to come in backside. We're going to talk about that on the page.
After iodine comes through, there's some partial plus left, and that's what's chlorine.
Reactions on the bottom half of the your water is going to compete. So, like, you could get mixed with the beer for that. Typically, when we do water, you can get more salt.
a smaller ring, I have a metal chip. What,
That's it. It's
which
just
one
like
will it
down.
do? Will it, like, is there a way to?
For us, if you can rearrange to a more stable cation,
This
you're
is
gonna do that.
With
Both of them, yeah, those one wasn't the same stability. It was both, they would have both been tertiary. It was one was a metal chip, one was a three.
Going from 7 to 6?
Yeah.
Okay, we didn't point something out. We need to point something out. So. Okay, guys, let's get started. Let's look back here. Someone brought up that when we rearranged here on the 7 to 6, when we rearranged, we went from what type of cation to what type of cation? Apparently, we went from tertiary to tertiary. Is that right? Is that right?
So we could have ended up.
there was another option for tertiary.
No, we didn't go from tertiary. You talking about this one here?
Yeah.
No, the original was secondary.
Yeah.
Then we rearranged.
But I'm saying if that one wasn't given, if that product wasn't given to you.
Oh, I know what you're saying. You're saying, why did we do the ring? Why did we move a methyl over?
Yeah, what determines like which
Okay.
one to do?
Yeah, let me go back. The question that's being asked down here is, back on this one, I hope I got the ring size right. We added the new H, is that a 7? We rearranged by moving this bond over and making 6. I think the question is, why not move the methyl over and rearrange, still have a 7, but we just rearranged by moving a methyl over. Is that the question? No?
Yeah.
Okay.
Because it's like both of them produce a tertiary, the same tertiary.
Both of them produce a tertiary, but this is still a 7. And if when we did this, we do a 6. Here's the take home here that I didn't mention. What are your best size rings? Your 5 and 6. 5 and 6 are your best size rings. See, in the 7, the ring is actually too wide, and the bond angle's beyond 109.5. So going the way we did, not only did it go to tertiary, but also went to a better ring. 5 and 6 are your best membered rings. Today, organic 1, also organic 2. Okay.
Is this something you would expect to see like still in significant proportions as a 7 versus a 4?
All this could be mixtures in real life. All this is really research. It could be solvent dependent, variety of things. That's why for us, the statement is, if you can rearrange to a better cation, do that. Better cation here would be 6-membered ring tertiary. Okay? You can also go to better rings, do that. You can rearrange to a 5 or 6, do that. 5 and 6 have your best bond angles. Lauren?
If 5 is just as good as 6, then why? How do you know that the cation went to the top and not, or and not to the bottom to make a 5-membered ring? Because if you had switched it to the positive was on the other side of the double bond.
Up here?
No, back on the 7 one again.
Uh-huh.
Instead of hitting it at the top to make it a 6-member, if you hit it at the bottom of the double bond, you get a 5-member.
If the original cation was down here,
Right, like.
well, because this going from here to here is a long distance shift. Typically the shifts are 1, 2 adjacent. Okay? I'm not saying that's not theoretically possible. It may be a wild product you find. For us, typically we're just going to move next door.
So if a cat of 4 will go to a 5 and a 7 will go to a 6, but not to a 5. 4 will go to a
In
6.
general, yeah. Ultimately, there may be lots of outcomes. But there's 2 types of questions. There's a show me the product. And you're like, well, is it 5? Is it 6? But there's also questions where I just give you the product and ask you to show me the mechanism. So obviously, if the product is a 5-member ring or whatever, then you do a mechanism to get that product. So there's 2 types of questions there.
And so if you say we take the products, would either of them be acceptable?
Is predicted by what?
Like, because if you do show the mechanism, there's only like real short answer. But if you say predict the product, would you accept either one as long as it's like a stable, viable structure?
I'd want you to show the one that had the most stable carbocation intermediate.
Okay.
So that's what we stated. That's going to be the major. Where are we at? Next page after the bromonium.
And the anti-trans.
Right here?
Yeah.
Okay, next page. How do we know it does not involve a carbocation? Mainly because of stereochemistry. For example, if you take cyclohexene and react it with chlorine, you add 2 chlorines to each, across the pi bond, 1 to each carbon. But we know you only get that. You only get trans. You do not get this. That's not formed. So our mechanism has to account for that and explain why we don't get that. Why do we not get that? Well, the mechanism, indeed, it does explain it. Let's do the mechanism, and I'll show you why we only get that. What's the first step? Are we going to make plus on top or bottom? Doesn't matter. This attacks chlorine, this off. And this is going to give new bond to chlorine. Let's say it hinged down, new bond to chlorine. Ah, but hold on. Well, let me draw it. New bond to chlorine and a plus. Is this actually formed, or what happens at the same time? This back bonds at the same time. This is not actually formed. The back bonding takes place, and we get this chlorine with a plus. All right? Nothing new there, right? That's what we just showed previously from the back bonding. But let's put in stereochemistry. You see, my rings don't always connect. It's like this. When I connect them, they didn't look too pointy. All right, that's it, yeah? And chlorine's bind there. There, each carbon is sp2. What's the hybridization now of each carbon? sp3. There are H's there. There's an H. Let's draw in the H's. All right? It's now an sp3. And so it's tetrahedral. Well, let's do that. Let's draw a tetrahedral. Here. Now that's 2 in the plane. The other, we're going to have 1 forward, 1 back. Well, the chlorine's like this. We can flip a coin. Boom. I want to draw the chlorine forward. Thus the H is what? Back. We could have did it the other way. Now, up here, that's also tetrahedral. The bond to this chlorine, do you want that forward or back? Forward. Why? Because it has to be. Okay? Right here. If this is a plane, and I'm bonded there, and you bond to me, are both bonds on the same side? Or are you somehow bonded on this side? They have to be on the same side. They have to both be sticking out. Like that. Now, what else is here? That. Okay? Has to be that. Now, it could also be the other way. It could also be both of them back and the H is forward. Either one. And it's actually a 50-50 chance, because this is side A and side B. Side B could be walking down the road, boom. And it all happens on side B. Or the molecule could have been like this. And boom, it all happens on that side. 50-50 chance. Because the alkene is planar. The chlorine could have come in from your side, or it could have come in from the Hall. If it comes in from your side, you get the bonds like this. If it comes in from the Hall, 50-50 chance. Okay? Now, at this point, now the other chlorine comes in. First off, is it going to attack top or bottom? In this case, it does not matter, because this is symmetrical. Does everybody see that? It does not matter. You get the same product. Let's say it attacks bottom. All right? How is it going to attack the bottom? Starts with a B. Backside. So if this chlorine is sticking out towards you, that's what the bulb means. How does the other chlorine come in and attack the carbon? It comes in from the Hall, because that's the backside compared to this. Or if it was this way, it would come in this way. This chlorine comes in here, and it kicks off the leaving group. And what does that give? Let's draw it over here. Let me actually draw it up here. How did this come in? Is this going to be dashed or bold? Good, be dashed. Now when that opens up, this bond just breaks, and it's up. But when that just does that, how's the chlorine? It's still bold.
So we knock that hydrogen forward?
And do it?
It knocks the hydrogen forward, the back one?
Yes, the H is actually forward. I'm not going to draw those in, but by default the H is forward, yes. Okay? But lo and behold, what's the relationship between two chlorines? Trans. You don't get this. Because this would only form if the chlorine came in front side. Okay? Now, what is the enantiomer? We'll cover that starting next week. The enantiomer is the mirror image. That's where everything is reversed. If the chlorine attached here, what would we get? How would the chlorine be down here? It'd be bold, and up here it would be dashed. But lo, it's also trans. That's actually the enantiomer of that. So when I say plus enantiomer, you get both of these. Why do you get both of these? Because you got both of these. Let's look at this. I just erased what I wanted to draw. Okay? Don't do that. What do we have here? We had the actual cation. Carbocation. Now let's draw some stereochemistry here, because that is tetrahedral. If there was a cation, and the chlorine just attacked there, I could have showed cation either place. How do we attack cations? We did this a day or two ago. I have a plus here. It's trigonal planar. How do you attack a cation?
Head on, upper BUC.
How do you attack a carbocation? Either side. Huh? That's just sitting there. Okay? If I told you to punch this paper, which side would you punch?
mean, if you had 100 gazillion papers in here and they're all presented to you, which side would you punch? You punch whatever side was presented to you. But it's all going to be random, okay? If you attack here, you're going to get two products. You're going to have chlorine here and chlorine forward, plus chlorine back and chlorine forward. Right? But if that was really a cation, you should get some cis product. But we know you do not get cis product. Why do you not get cis product? Because it's really not a cation. It really involves this attacking the backside of the chloronium. And when you do that, you only get trans. That's why you only get trans. Okay?
Is there a theory why that backside attack is favored, since it has to move 109 degrees?
Why is it favored over what?
Over front side attack, especially in this example. Because that gives the strain on.
Okay, hold out your chlorine. Okay, I need to attack you. Move your chlorine, you're in my way. So how is it better to attack him? I'm going to go around the backside, away from that chlorine, attacking backside. The chlorine's in the way. Okay, that's why you attack backside. What's around the chlorine? Electrons. What's around my chlorine? Electrons. You're in the way. Okay? This chlorine's forward. It's like, so I'm going to come in from the hall and attack backside because of that. Okay, all that's explained down low, written out there. Next reaction, formation of trans halohydrins. This is going to be a reaction with X2 and water. If you include water, you get a different outcome. Water acts as a nucleophile. A halohydrin is when you have a OH and a halogen in the same molecule. Called a halohydrin. Halo from the halogen, hydrin kind of from hydrate or the OH group. Let's do the mechanism and we'll see what else is formed here. First step is, well, alkenes don't react with pure water. They will react with chlorine. When this reacts with chlorine, what do you get? Chloronium ion. Okay? I'm not going to show mechanism to get to that. We've already done that. All right? Now there's Cl minus here. We also have water. And when you include water, you want to use it. Now you could debate why does the chlorine not attack and you get a dichloride. If you have water here, use it. Water attacks, but it attacks the same place. Are you going to attack on the left or right? Left, because there's more plus is going to be here. Because this has more rich friends, you could argue that, but you attack the more substituted side. Water attacks here, leaving group gets kicked off. What do we get? Chlorine just got kicked off. What's now bonded here? The O, but it has two H's and a plus charge. And now, to get a final neutral product, we can show the Cl minus taking the H. These electrons take the H. These electrons stay behind on oxygen. And what does that give? That product plus what's the byproduct? Yeah, you do also form HCl for a completely balanced bond reaction. Okay?
So we have a carbon with 2 methyls and an OH, and then we have CH2Cl. Questions about this one? It's called a halohydrin. Whenever you have water added with a halogen, you get the water attacking. So the mechanism is very similar. Most all the mechanisms we do are very similar. If you learn the general trends, you just do what needs to be done. Okay? Predict the products below. First let's do this one. We have a ring here, bromine in water. First off, we know we're going to make bromohydrin. So on a flashcard, you can maybe show this with no product on the backside or something. So the rings, typically, we have stereochemistry because things can't rotate. And here we get this product as shown. The Br and the H are going to be trans. That's why up top we called it a trans halohydrin. Why are they going to be trans? But what's the intermediate here? What does water attack?
That's the bromone.
Let me draw a bromonium ion and put this methyl here. This is what's formed. Now water attacks. Are we going to attack top or bottom carbon? Top, we're substituted, so this attacks here. Kicks off the leaving group. But we got stereochemistry defined here. The leaving group, is it forward or back? It's going to the Hall. Okay? So here's the board, and it's going to the Hall. Since it's going to the Hall, how does the water come in? Ground from the front. We call that backside, even though we're saying front. It's backside compared to this. Okay? So when we draw the product, Br just gets kicked off, but that bond's still the same. Up here, how's the oxygen going to be? Dashed or bold? Bold, because it came in from the front. So we got this here. Now by default, how's the methyl now? Methyl is now back. Why is it back? Well, let's do our little attack again. Here. The Br is actually back. The methyl's forward. Okay, methyl is black. Methyl's black. Br is going to the Hall. Okay? There it is. The Br, okay. Connor, you're going to attack this carbon and we're going to keep that off. How are you going to attack it? There you go. It's presented to you like this. How are you going to attack it? Why not just like here? So that's our backside to the leaving group. There's the leaving. Backside is here. Okay? So attack it. There you go. Attack it with that. Okay? Right here. It kicks this off, but at the same time, it also pushes this back. Okay? That's why the methyl ends up changing. That's called Walden inversion. We'll cover that during test 3. In the end, if you got this forward, by default, that has to be back. See, it came in front and pushed the methyl back as it pushed everything off. There you go. Then when we just lose the H, we get this. What takes the H? Well, here you had a minus. That minus didn't attack. It takes the H. You get that plus HBr. You also get an enantiomer. When you look back at this, you can do the enantiomer. The enantiomer is just going to be where everything's reversed. Well, I could have drawn this forward and that dashed. Okay? Questions about this mechanism? Aaron?
Is there ever a time where like the methyl group would be too large that it wouldn't do the backside?
No, I don't think so.
Because the stereochemistry said that on the VR?
Sterics can influence things.
Okay,
Nothing in right now that we're covering.
okay.
Okay. Predict the products down below. I'm going to ask you to do those on your own, and we'll look at those first thing next time. Okay? The one thing we'll do is just consider stereochemistry when needed. We're going to have to sort of further define when it's needed and when it's not. Basically, it's needed whenever the product can have sterilizers. I mean, back up here, that can't have a sterilizer. So there's nothing to consider. But down here, it can. Because, for example, the OH and the BR could be cis. But we don't get that. And you also get an anti. So you have to realize that. And as we move into stereochemistry next week, we'll do more and more of this. And as you look back, okay. We'll do those down there. Let's move to the next reaction. What have we covered on the yellow sheet? We've covered X2 and X2 with water. I think next we're going to look, well, we'll make our way around down there. Epoxides. An epoxide is it's really an ether. It's a cyclic three-membered ring ether. Oxygen bonded to carbon. It's called an epoxide. You may have heard of epoxy glues. Okay. We will see consistencies in all of our mechanisms. The consistency here is, where did we just see a three-membered ring with a heteroatom? Bromonium ion, chloronium. It's going to be very similar to that. Except the oxygen can go neutral, and so we can just be left with that ring. So how do we form this guy? First off, what type of reagent? The reagent is going to be a peroxy acid. That's what we react with. Shown condensed like this, or like an OO is a peroxide. In fact, what is this here? Hydrogen peroxides in your medicine cabinet. Okay. We just have made this carbonyl, and it looks like a carboxylic acid, peroxy acid, condensed like this. R being generic, it can be anything. It could be a methyl, it can be a benzene ring. The most common peroxy acid is when it's a benzene ring and a chlorine in the meta position called metachloroperoxybenzoic acid. Should be in your textbook, MCPBA. But just consider that's just the R group. And so we can come over here. The two oxygens bonded together is similar to the two bromines bonded together in Br2. We can show that here. The difference is we got this carbonyl, very polarizable pooling. Because that pulls, this pulls. Because that pulls, this pulls. So this oxygen actually has some partial plus. And that's the oxygen that the pi bond attacks. And so the pi bond, are we going to leave plus on left or right? On the left. So this hinges away, it attacks that oxygen. When it attacks it, we're going to kick off the leaving group. Well, this is covalent. What does that give? Well, we just attack the oxygen has an H on it. So it gives this. Everybody agree? Kind of in there? Is this actually formed, though?
No.
Let's see that. Why is it not actually formed? Because here's the take-home. Anytime your new thing has a lone pair, it's going to immediately back bond. Bromine and chlorine did. This has a lone pair. Those electrons are going to be attracted to the plus. So it's not actually formed. And what do we get when it back bonds? We get a structure that looks like this here. That's analogous to our bromonium ion. The difference is this can go neutral by losing an H. The thing that got kicked off was like acetate. It can act as a base, take the H, electrons stay behind, and if you just simply do that, what do you get? You get your three-membered ring that's going neutral, and that actually can be isolated and made. Yes, it does have ring strain, but three-member rings can be made. Called an epoxide. You see the similarities in the bromonium ion? Now in organic 2, you may be wondering, can we attack here and open this up? You can. But we're not going to do any of that chemistry here. We do chemistry of epoxides in organic 2. Right now we're just making them. I drew it up there. Here it is with the byproduct. Questions about the epoxide mechanism? So you can predict the products down below. Let me do one for you and I'll let you do the others on your own over the weekend. Okay. This is a predictive product. When you do predictive products, the first thing you have to do is you have to say, okay, what type of reactivity do I have? For you guys, all we've done so far is alkenes, so you kind of zero in on that, right? I mean, this boring hydrocarbon. That's going to attack something. Well, what is MCPBA? Most common peroxy acid. What do peroxy acids do to alkenes? They make epoxides. And in terms of making a peroxide, an epoxide, well, that's just what? Used to be an alkene, now it has oxygen. Did you recognize that all we did was just have an oxygen bond into each carbon? Right? And that's it. What I'm recommending, guys, is just boil it down to what are we doing here? I mean, simply, alkenes react with peroxy acids, make epoxide. Any questions about that product? Sophia, question? Y'all seem stunned about that outcome.
I have a question. So are all of the epoxides just going to look like that? All of every screen?
What do you mean, a three-member ring with an oxygen? That's what epoxide is.
So we don't have to, but we have to show the mechanism.
This wasn't a mechanism question, this was a predictive product. Remember, there's two types of questions here. I just asked you for the product. Should you know the mechanism? Yeah, you could be asked to show the mechanism. I didn't ask you to show the mechanism. What I would suggest you do, though, is use your mechanism to predict product. But see, some reactions are almost easily memorizable, but you got to be careful. You also need to know mechanism. So people say you don't memorize organic chemistry. There is a little memorization. Here's a memorization. Alkenes react with peroxy acids to give what? Epoxides. But then on the back of your note card, you have all the details. For example, if we had stereochemistry, what would we do? Well, we need to look at it more. And we need to do the ones down here. And you need to be able to look out for stereochemistry. I said consider stereochemistry. Can you deal with stereochemistry? We did some examples on the previous page. Okay, for example, that carbon now is tetrahedral. How many H's on that carbon? One. Tetrahedral. So if these are the plane, is the oxygen bond doing a drop forward or back? Okay? You can draw it forward. Now, I'm not going to draw that one forward at all for a particular reason. But you can also draw it back. That's going to be 50-50. Why is it 50-50? Because this, okay, we're doing that one up there. Because that's planar, the alkene is planar, it's walking down the road. Okay? And it sees an oxygen here, it's bonded to another oxygen, but it's got some partial plus. And it attacks that oxygen. But at the same time it attacks the oxygen, what does the oxygen do? It back bonds. So I'm going to do back bond, but at the same time. And there's the three-membered ring, but you got an H on you. So somebody has to take the H off, and we got the three-membered ring. Forward, it has to be forward. Okay? But maybe I'm walking down the road, and instead of the peroxy acid being on my right side, the forward side, maybe the reagent's over here. Could it be over here? If I'm in the flask, there's millions of molecules, yeah. And it all happened this way. The oxygen bond could be forward or it could be back. It's 50-50. Here the oxygen bond's forward, there it's back. Why did I show it here, not here? We'll have to see it moving as we move forward. Because that's chiral. There it matters. It doesn't matter there. We'll have to learn that next week. Okay? These are the ones below. Think about stereochemistry, and what I would like to see is Monday, you're like, I considered stereochemistry here and I got stuck here. Tell me what I did. Then you'll be ready to hear the answer and you'll go, oh, okay, I see now. Okay? Please work through. Please look at the rest of what we see here with the guide being your yellow. Okay? We've got 4 more reactions to cover and they're pretty in-depth. Boron, mercury, y'all got an appetite? Oh.